Hello everyone, welcome back to the MP Coding FreeRTOS Synchronization Primitives series. In my previous two videos, we talked about binary semaphores and counting semaphores, along with some examples. In today's video, we'll continue with mutexes and recursive mutexes. As we discussed earlier with the binary semaphore, a mutex is quite similar, but with one key difference: ownership. A binary semaphore doesn't have ownership, any task can take it, and any task can release it. But a mutex is ownable. The task that locks the mutex must be the one that unlocks it. This ensures proper control and prevents other tasks from accidentally releasing the mutex. Now, let's look at the lock and unlock operations. When locking, if the mutex is free, the task locks it and enters its critical section. If it's already locked, the task will be blocked until the mutex becomes available. When unlocking, the owning task releases the mutex, allowing another waiting task to acquire it. Just like the binary semaphore, the mutex also supports priority inheritance. If a low-priority task holds a mutex while a high-priority task is waiting for it, the low-priority task temporarily inherits the higher priority. This mechanism prevents priority inversion, where a medium-priority task might otherwise starve the high-priority one. Alright, let's move on to the STM32 example. As usual, I'm using the STM32 F429 discovery board, and the system clock is already configured. So, let's get started by enabling FreeRTOS. In the FreeRTOS configuration, to use a mutex, we first need to make sure it's enabled in the kernel settings. If we take a look here, you can see that Use Mutex is enabled by default, so we don't need to change anything. Next, if we go to the Mutex tab, we can see two tables, one for mutexes and another for recursive mutexes. If you're using the CMSys API, you can add a mutex here, and CubeMX will automatically generate the mutex handle and its creation code for you. But as I've shown in previous examples, I'll be using the native FreeRTOS API, so I won't define a mutex here. It's generally a good practice to use the native FreeRTOS API instead of the CMSys layer. Then, moving to the Tasks and Queues tab, you'll see the default task. We can't delete it from CubeMX, so, as before, we'll remove it manually after the code is generated. Next, as usual, I'll enable UART1 to print messages to the serial console. I'll configure pins PG13, PG14, and PG11 as GPIO output pins. These pins are connected to my logic analyzer. I'll also set PA0 as a GPIO external interrupt pin. This is connected to the onboard push button. Then, in the NVIC settings, I'll enable the GPIO interrupt and set its priority to 7, which is below 6. As I've explained before, we use a lower priority here for proper interrupt handling with FreeRTOS. Another important step is to change the time-based source to a timer other than system tick. That's because system tick is already used by the FreeRTOS kernel. If we don't change it, it can cause conflicts. So, just select a different timer here to avoid any issues. Alright, that's all for the CubeMX configuration. Let's go ahead and generate the code. Since I'm not going to use the CMSys layer, let's open the CMSys file and copy the native FreeRTOS header includes. Then, in the main.c file, I'll remove the CMSys os.h include and paste the copied FreeRTOS includes instead. For this example, we only need three header files: FreeRTOS.h, task.h, and semford.h. All the mutex functions are handled through the semford.h header. Next, I'll remove the CubeMX generated default task handle and its entry function. And in the main function, I'll also delete all of the task creation code that CubeMX generated, because we'll be creating tasks using the native FreeRTOS API instead. Alright, let's start coding. Here, I've already written the code, so let's take a look. This part is very similar to the binary semaphore example, so nothing fundamentally new here. First, I've created a variable for the mutex handle, and also handles for two tasks, task 1 and task 2. Next, we have the task entry functions. In task 1, inside the loop, the task first tries to take the mutex. If the mutex is free, task 1 locks it, executes its code, toggles GPIO PG13, waits for 500 milliseconds, and then unlocks the mutex. After that, it goes back to the beginning of the loop. Task 2 is essentially the same, but it toggles GPIO PG14 instead. In the main function, we first create the mutex using x semaphore create mutex and store the return value in the mutex handle variable. We also print the result to the serial console using UART. Next, we create the two tasks using x task create. As I've explained in previous video, we need to pass the task entry function, task name, stack size, parameters, priority, and finally the reference to the task handle. In this example, we're not passing any parameters, so they are set to null for both tasks. The priorities are set so that task 1 is higher priority and task 2 is lower priority. Finally, start the scheduler. That's all for the code. Now, let's look at the behavior. Run the program. And let's look at the logic analyzer timing chart. You can see that GPIO13 is toggling, which means only task 1 is running. Task 2 stays in forever waiting mode. Why is this happening? It's similar to the semaphore example. Since task 1 has higher priority, it keeps taking the mutex at the start of each loop cycle and runs continuously. As a result, task 2 never gets a chance to run. One simple way to fix this is to add a small delay after releasing the mutex, which gives task 2 a chance to take the mutex and execute. Here, I'm adding a small 10 millisecond delay to give task 2 a chance to take the mutex and run. Also, just before releasing the mutex, I'll add a GPIO toggle in both task 1 and task 2. This way, we can clearly see the task activity on the logic analyzer. Now, let's run the code. You can see that task 2 is also running now. Here's what's happening. First, task 1 takes the mutex and runs, while task 2 is blocked, waiting to acquire the mutex. After 500 milliseconds, task 1 releases the mutex and enters the 10 millisecond delay, giving task 2 a chance to take the mutex. As soon as task 1 releases it, task 2 takes the mutex and runs for 500 milliseconds. Then, after the 10 millisecond delay, task 1 becomes active and tries to take the mutex. Since task 2 is still holding it, task 1, even though it has higher priority, must wait until task 2 releases the mutex. After task 2 releases the mutex, task 1 runs again. This mechanism is called priority inheritance, where the lower priority task temporarily prevents priority inversion, ensuring proper task synchronization. Okay, let's check how ownership works. Since I've already set up the push button as an external interrupt, I'll try to release the mutex from the ISR, just like we did with the semaphore example. I've also added a GPIO11 toggle inside the ISR so we can verify whether the interrupt is actually triggered. In the ISR, I'm releasing the mutex, and I've commented out the mutex release lines in both task 1 and task 2. Now let's run the program and see what happens. When the program runs, task 1 executes once and then goes into a blocked state. Task 2 remains blocked as well. So when I press the push button, you can see GPIO11 toggles once, and then nothing happens. That's because the ISR can't release the mutex, since only the task that owns the mutex is allowed to unlock it. And if I press the button multiple times, you'll notice that GPIO11 no longer toggles. This means the ISR was triggered only once, and after that, it stopped responding. This happens because the external interrupt is still active and was never cleared properly. Since the ISR didn't actually release the mutex or complete its intended work, the system never exited the blocked state, leaving both tasks stuck waiting for the mutex. As a result, the interrupt line also gets stuck, and no further interrupts are serviced. In short, the program is blocked because the mutex is never released, and the interrupt is effectively disabled due to the pending state. That's all for the mutex. Now, let's quickly look at the recursive mutex. Recursive mutex, special kind of mutex that allows the same task to take the mutex multiple times, as long as it gives it back the same number of times. Useful in cases where a function that takes a mutex is called by another function that already holds it. The normal mutex same task tries to take the mutex again before releasing it, it will block, because the mutex is already owned, even though by itself. A recursive mutex solves that. If a task already owns the mutex and tries to take it again, it will succeed, but block count increases. The task must then give the mutex the same number of times it took it. A recursive mutex keeps track of two things. First is which task currently owns it, the owner. Second is how many times that owner has locked it, lock count. Only the owner task can retake the same mutex multiple times. The mutex is only considered free, available for other tasks, when the lock count reaches 0. If a different task tries to take the mutex while it is owned, no matter what the lock count is, it will block or fail if a timeout is used, because recursive locking applies only to the owner task. Recursive mutexes are useful when function that locks a resource may call another function that also locks the same resource. As examples, log message locks the UART mutex. Inside log message, it calls format message which also tries to lock the same UART mutex. Without a recursive mutex, the task deadlocks on itself. With a recursive mutex, it's safe. Okay, now let's look at the recursive mutex example. First, you need to enable recursive mutexes. In CubeMX, open the FreeRTOS configuration and enable use recursive mutexes, then generate the code. If you prefer not to use CubeMX, you can enable this in your FreeRTOS config.h file by setting config use recursive mutexes to 1. In my main.c I've renamed the handle to recursive mutex handle and created the recursive mutex using x semaphore create recursive mutex. Task priorities remain the same. Task 1 is the higher priority task, and task 2 is the lower priority task. Now let's look at the task code. This is where the recursive behavior appears. In task 1's loop we call function A. Function A tries to lock the recursive mutex. If the mutex is free, it locks it and the recursive lock count increases. Function A then toggles pin 14, logs a message over UART, waits 500 milliseconds, and calls a nested function B. Function B also takes the same recursive mutex. Because this is a recursive mutex, the nested take succeeds, the lock count increases again. Function B toggles pin 13, logs another UART message, waits 500 milliseconds, and then releases the mutex, which decrements the lock count. After function B returns, function A finishes and releases the mutex again, decrementing the lock count a second time. Finally, task 1 waits 2 seconds before repeating the loop. Task 2 simply tries to take the recursive mutex. If it succeeds, it toggles pin 11, waits 1 second, releases the mutex, and then waits 3 seconds before trying again. That's the complete flow. Task 1 demonstrates nested locking using a recursive mutex, allowing the same task to lock the resource multiple times safely. Task 2 shows a separate task attempting to use the shared resource. Alright, let's run the program and check the logic analyzer. On the logic analyzer and the serial monitor you can see function A, function B, and task 2, all are running. I've added markers to the timing chart to make this easier to follow. Here's what happens step by step with serial log. At the start, task 1 runs and calls function A. Function A takes the recursive mutex and locks it. After 500 milliseconds, function A calls function B. Function B takes the same recursive mutex again. The recursive lock count increases, allowing nested locking by the same task. After another 500 milliseconds, function B exits and releases the mutex. The lock count is decremented. Function A then releases the mutex and returns. At this point task 1 waits 2 seconds before the next iteration. Next, task 2 acquires the mutex, toggles its pin, waits 1 second, releases the mutex, and then waits 3 seconds before trying again. After task 1's 2-second wait, it attempts to take the mutex again. By then task 2 has already released it, so task 1 successfully takes ownership. If task 1 had tried to take the mutex before task 2 released it, task 1 would have been blocked until the mutex became available. Even with a recursive mutex, ownership rules still apply. The same task can take the mutex multiple times, increasing the lock count, but other tasks must wait until the lock count reaches 0 and the mutex is fully released. Today, we explored mutex and recursive mutex in FreeRTOS, understanding how ownership works and how multiple locks are handled within the same task. We also looked at how other tasks must wait until the mutex is fully released before acquiring it. In the next video, we'll dive into event group synchronization primitives with practical examples, so you can see how they can be used for more advanced task coordination. If you found this helpful, don't forget to like, subscribe, and share. Thanks for watching, and I'll see you in the next one.